Welcome back to my new video on lattice energy. Lattice energy is maybe a new concept for some of you. I'm assuming that you already know how to deal with Hess cycles and Hess's law. So the idea of lattice energy, it tells us about the strength of ionic bonds. We can only get limited information from an enthalpy change of formation. You might be able to think of a reason why now. Pause the video if you like. The reason for limited information is that enthalpy change of formation deals with the elements, so we need to break them apart, turn them into ions before we can make the ionic solid. So a better quantity to measure is the lattice energy, or the lattice enthalpy. So the full definition of the lattice energy is it's defined as the enthalpy change when 1 mole of an ionic solid is formed from its gaseous ions. Now, unfortunately, it can't be measured directly, so we need a new form of the Hess's cycle to be able to calculate it indirectly from experimental results. Apologies for the pen in the background there. So, we're going to start making our Hess cycle. We'll start it from very first principles. Okay, we're going to start from the enthalpy change of formation. There we go. Just to remind you, so we've got delta H, standard symbol, and F for formation. So the example we're going to take is for sodium chloride. So if we look at the enthalpy change of formation, we need to form 1 mole of a compound from its elements in their standard state. So there we've got sodium solid, half Cl2. Okay, that's going to make NaCl, 1 mole of NaCl solid. Okay, and there you go. I'll put in again delta HF for you there. Okay, on the other side, we're going to put in what is the lattice energy. So nice big arrow to downward arrow to show that it's going to be exothermic. Okay, and our definition, it comes from the gaseous ion. So it's going to be made from Na plus and Cl minus, both in the gaseous state. So now in our new version of the Hess cycle, we call this a Born-Haber cycle. We're going to go around in the opposite direction because we need to take a different route. So there's a number of different enthalpy changes for this. The first is the enthalpy change of atomization. Now the first one I'm going to do here is taking Na and turning it into a gas. Okay, so it's just gaseous atoms. Okay, so the first enthalpy change there is the atomization for sodium. So we made Na gas and half Cl2 gas. Second one again is another atomization. So this time we're going to still have Na gas, but this time we need to break apart the Cl2 molecules. Half Cl2 will give us Cl gas. Next up is ionization energy. There we go. So ionization energy for sodium. So the ionization energy to remove 1 electron. So it's going to turn that into Na plus. And then we've still got Cl gas. Okay, if I label that in there, that's delta H standard, i.e. ionization energy for sodium. The next step round, okay, is changing the Cl gas to Cl minus. This one we call delta H Ea, that's electron affinity. So when an atom gains an electron, it's electron affinity. When it loses one, it is an ionization energy. And there you go, the last label goes in, delta H lat for lattice energy. And there you can see the full Born-Haber cycle there. So it's a special case of the Hess cycle. Okay, now we can, apologies for changing the page, but now we can write out the full equation, okay, for our Hess cycle. So the enthalpy change of formation is equal, if we go round the other side of the cycle, remembering back to the last page there, so it's the enthalpy change of atomizations, both of them in that case, and the enthalpy changes of the ionization energy. There we go. And then the enthalpy change for the electron affinity, Ea, we'll just put that in. Excellent. And the final step is the lattice enthalpy. There you go. Okay, so that would give us, that formula is the full round the Hess cycle the opposite way. Okay, what we really should do though, most of the time we're going to be looking for the lattice energy, so I'll rearrange it for the delta H standard lattice energy. It may take a little while to just write that up, but it is, so the enthalpy change for lattice energy is equal to the enthalpy change for formation, take away the enthalpy changes of atomization, then enthalpy enthalpy change for ionization energies, and finally the enthalpy change for electron affinity. You can probably see just by looking at that the delta H lat is always going to be a negative number. There's a lot that we're taking away there from the enthalpy change of formation. So delta H lat is always, apologies for the handwriting, is always negative. So it's always going to be exothermic. Just come up there, exothermic, excellent, okay. And of course, the magnitude of how exothermic it is, the more exothermic, then that means a stronger lattice. Less exothermic means a weaker lattice. So a couple of notes when we're looking at enthalpy changes. So for a 2+ ion, when we're making the Born-Haber cycle, to make a 2+ ion, we need 2 ionization energies, 2 successive ionization energies to remove the 2 electrons. Okay, so that's going to have to go into the Born-Haber cycle. I'll just write it up there. So 2 ionization energies are needed. And for a 2- ion, then we will need 2 electron affinities. Interestingly enough, you will always find that the first electron affinity is exothermic. The second one is always endothermic, because the second electron is having to be pushed into an ion that's already negative. There is repulsion there, so you need to add energy to the system to allow it to accept that electron. Okay, so the second electron affinity is just writing up there. Second electron affinity is always positive. It's always endothermic because of that repulsion there. Okay, so it's a quick whistle-stop tour on lattice energy and a simple Born-Haber cycle, just to help you revise the concept. Thanks very much for listening, and I hope to see you on the next video. Thanks very much.